Here are the answers for example 2 and example 3. HBr is a strong acid following rule number 1. Bromine is a halogen. Molecule number B is a weak acid following rule number 2. It is an oxyacid, but it does not have enough oxygens to be strong. Molecule number C is a weak acid. It is because it has COOH in the formula, meaning that it's a carboxylic acid. And molecule D is a strong acid following rule number 2. It's an oxyacid, and it has 2 more oxygens in the formula than the hydrogens. Molecule E. It's a strong base. It's an oxide, and it has a metal that is in group 2. Molecule number F is a weak base. It is a hydroxide, but iron is a transition metal. It's not found in group 1 or group 2. KOH. It is a strong base because potassium is in group 1. And finally, zinc oxide. It is a weak base because it's an oxide with a metal not in group 1 or 2. Example 3. Circle the chemical that is stronger in each pair. For A, because HClO4 has more oxygens, it is stronger. For B, because I is lower than Cl in the periodic table, HI is a stronger acid. And for C, Sr is in group 2, meaning strontium oxide is a strong base, where copper is a transition metal, so it would be a weak base. Because strong acids and bases dissociate close to 100%, the concentration of the ions they produce can be calculated using mole ratios in the ionization equations. Here's an example. Determine the H+ concentration of a 0.25 mole per liter HCl solution. Always start by writing an ionization equation. HCl is an acid because it has an H listed first. Therefore, it will make H+ ions. If I have a 0.25 mole per liter HCl solution, I can use a mole ratio to go to the H+ concentration, because HCl is a strong acid, meaning that in my system it will all fall apart into H+'s. Because I have a 1:1 mole ratio, I will have a 0.25 mole per liter H+ solution. Try out example number 2. Determine the hydroxide concentration of a 1.5 mole per liter magnesium hydroxide solution. Pause the video now until you get your answer. Here's the answer for example 2. Again, start by writing an ionization equation. Magnesium hydroxide is a base. That means it will make OH1- ions. and two of them can dissociate. If I have a 1.5 mole per liter solution, in order to convert into hydroxides, I have to times by a 2 to 1 mole ratio. That means the concentration of OH1 minus in my solution will be 3 moles per liter. Soren Sorensen developed a more convenient way of describing how acidic or basic a solution is instead of reporting the hydrogen or hydroxide concentrations. He developed the pH and pOH scale, which are exponential scales based on the power of 10. Therefore, one step on the pH scale is 10 times more acidic or basic than the previous value. Sorensen defined pure water as having a neutral pH. Water undergoes the following reaction with itself to produce H3O plus and OH1 minus. H3O plus is known as a hydronium ion. It is equal in acidity to an H1 plus. The reverse reaction in this equilibrium is favored. In neutral water at 25 degrees Celsius, the hydronium and hydroxide concentration is 1 times 10 to the minus 7 moles per liter. The equilibrium constant for this reaction can be calculated using the following expression. Kc equals the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to those coefficients. Now, the concentration of any pure liquid or solid in an equilibrium doesn't change, so they're eliminated from equilibrium expressions. We have two pure liquids in our equation, both being water. If we ignore those in the equilibrium expression, we can no longer call it a Kc. We then call it a Kw, because this is the equilibrium constant for water. If we sub in the value of the concentration of these ions at 25 degrees Celsius, we can solve for the value of Kw. This is an important expression. Sorensen based his pH and pOH scale on this reaction. Kw is known as the ion product for water. This equation shows that there's an inverse relationship between the amount of H plus and OH1 minus in any solution. Therefore, acids can be described as any solution with a hydrogen ion concentration greater than 1 times 10 to the minus 7 and a hydroxide concentration less than 1 times 10 to the minus 7. Bases have the opposite. And neutral solutions have hydrogen and hydroxide concentrations both the same value, equal to 1 times 10 to the minus 7. The pH and the pOH scale are related to hydrogen and hydroxide concentrations using the following 5 equations. To calculate the pH of a solution, you take the negative log of the H plus or H3O plus concentration. Mathematically, taking a log calculates what exponent to the base 10 would you need to get a particular number. Now, because hydrogen ion concentrations are so small and usually have a negative exponent, Sorensen threw a minus sign in front of the log to make the pH scale have all positive numbers. In order to reverse this equation or rearrange it, if you want to find the H plus or H3O concentration, you take base 10 and have the exponent minus the pH. The pOH scale is the mirror to the pH scale, except that it measures hydroxide ion concentrations. The equations look very similar, just involving the different ion. An interesting relationship appears between pH and pOH. Both values added together always equal 14. Let's have a look at both scales. Since water at 25 degrees Celsius has a hydronium concentration and hydroxide concentration of 1 times 10 to the minus 7 moles per liter, it is 7 on both the pH and the pOH scale, because the negative log or the exponent changed to a positive value would be 7. That's why 7 is defined as being neutral. As discussed in previous courses, a pH that is less than 7 is acidic, and that is greater than 7 is basic. On the pOH side of the scale, you see the opposite. If you have a pOH greater than 7, it's an acid, and less than 7, it's basic. Also notice that if you take any pH value and add it to the pOH value, you will get 14. Since concentration determines pH and pOH, values can be higher than 14 and lower than 0, which means it is possible to have negative pH and pOH values. It is a misconception that the scale only goes from 0 to 14.